So now we'll study polarization by double refraction. Okay, so you see, when we'll be doing polarization by double refraction, the double refraction phenomena, as I told you, it was introduced by Bartholinus. Okay, Bartholinus. All right, around say 1669 or 70, something like that. During that study, during that time, well, crystals of calcium carbonate, CaCO3, which is also called Iceland spar crystal, okay, they show some peculiar phenomena. What is it? When light is incident on this kind of a crystal, suppose say this is your crystal under study, all right. So when you allow light to fall on this crystal, all right, well, it breaks up into two parts like this. The moment it reaches the surface of the crystal, it breaks up into two parts. The one part has polarization in one direction, and the other part has polarization, say, in a mutually perpendicular direction. It goes inside. Okay, all right, and then it emerges like that. From the crystal as two rays. All right. Now this is, suppose say, your calcite crystal, calcium carbonate, the same thing. Okay. All right. And this ray we call the extraordinary ray, E ray, and this is the ordinary ray, O ray. Now what is the difference between the two rays? Well, an ordinary ray obeys Snell's law, and an extraordinary ray does not obey Snell's law. Okay, now this phenomenon where an incident light, okay, breaks up into its two components of ordinary ray and extraordinary ray is called birefringence. This is very important. Birefringence, okay, or double refraction. And the crystal is said to be birefringent crystal. Now, this kind of phenomena is exhibited by all transparent anisotropic materials. Materials have to be anisotropic. So, two rays formed in double refraction, both are linearly polarized in mutually perpendicular direction. Now, how do you know which one is your E ray and which one is your O ray? So, if you take a piece of paper like this, on which you place this crystal, and if you put a dot, and now if you rotate the crystal, well, for O ray you will see the dot remains in the same position, but for the E ray the dot keeps on moving around this point. Okay, so as you rotate the crystal, the E ray will show the dot moving in all directions. That means instead of one dot, if you make one pen dot, the moment you place the crystal, you will see two dots, one for E ray, one for O ray. Okay, and then when you move the crystal, you will see the dot for O ray will remain constant. It obeys Snell's law, but the dot for E ray will keep on changing. That is the proof. Now this phenomenon of double refraction has been made to design a polarizer and an analyzer in the form of a prism called Nicol prism. Now what is Nicol prism? It is made from calcite crystal. Okay, so this was used to produce linearly polarized light. Alright, and also to analyze the state of polarization. That means you can have Nicol prism both as polarizer as well as an analyzer. So you see, this was actually the Nicol prism. You get it as short note. If you are sitting for your exam, then you might get short note on Nicol prism, or you might get MCQs, also short MCQs. So this was discovered by William Nicol. All right, 1820, in 1820. All right, so actually, so you have a calcite crystal like this. Okay, so it is cut, actually it is cut from a calcite crystal like this. It is cut like this, and then after cutting it, the crystal is, suppose you cut it along this line, say Mn. If you cut it along this line Mn, and then if the two pieces are again cemented together, if you join the two pieces together along the same line by using cemented by using Canada balsam. You use this glue to cement the two calcite crystals which are cut in this manner. Okay, now the refractive index of Canada balsam, the refractive index of Canada balsam is between the refractive index of O ray and E ray. It is around 556 or 550, lying between the refractive index of O ray and E ray. This is the typical basis of the design, that the refractive, that is why they choose this Canada balsam, that the refractive index lies between the refractive index of O ray and E ray. Okay, all right. So for an appropriate choice of the direction of the incident ray, the E ray passes through the prism while the O ray suffers reflection at the balsam layer. So suppose, say, so if you have, say this is your optic axis. Okay, so what happens over here is the following. So light comes from here. One component passes through and the other component gets reflected from here. Okay, so if you call this your optic axis, if this is your optic axis, okay, all right, so this is 48 degrees, all right, this is 68 degrees, all right, this is 22 degrees. Now the E ray which comes at this point, it gets separated and then it passes through the crystal. It is the O ray which gets reflected, which should be perpendicular. It's mutually perpendicular to the E ray, isn't it? So the O ray gets reflected from out of the crystal. So the crystal, these prisms, they are considered as very good polarizers, and well, they exhibit selective absorption. Okay, though they are very good polarizers, they have a very limited view, but these crystals exhibit selective absorption and double refraction. So here the O ray is the one which is completely absorbed and the E ray passes through. So this is the principle of Nicol prism. You may get it as your short note, and this is used both as a polarizer and an analyzer. So today now we will discuss Malus law and we will complete or finish our class today for polarization. The rest of it we'll do on Tuesday, and we'll do some important questions and problems on polarization. Okay.